this presentation, this is about benchmarking exact value analyses. So I can skip over the agenda very quickly because you'll see this during the talk. This work has mainly been done by Marc Miltenberger, who is one of the PhD students in my department, so all the fame goes to him actually, but unfortunately he cannot be here today, so it is my duty to present this work. Now, before we talk about value analysis too much, we should first understand what a value analysis is. You see this piece of code, and since we're security people, we often want to find out whether there is a vulnerability in it. So we ask questions like, you initialize a secret key spec, so there is a cryptographic key going into this. Is this something that is hard-coded? So we ask the value analysis, give us the concrete value, and if it statically comes back with a value, we know we are in trouble. However, this is not super easy, because this is not actually static in terms of here is the value. Because to get this correct key, I would need to know what get bytes does. Only then I can reconstruct the actual byte array that is my key. I need support for things like fields in that case, because this is read out of the field here. And there are things going on like string concatenation. This URL is hard-coded. My analysis can give it to me. It's not a problem. However, to find the real URL, I have to support string concatenation. And this can get a lot more complex if, for example, someone would implement SHA-256 hash on his own, put some value that is in the code as a constant through this SHA implementation, and then concatenate it here for whatever reason. If I want the final value, I would be able to know what all of this is, and then say, this is the correct hash. So value analysis is far more than just grabbing for constants here. And we have seen this. I think this comes out of one of the Android apps we have analyzed. So people obfuscate their apps. They don't want you to know to which server they are connecting. So they do some mumbo jumbo here, which essentially is not real crypto, because everything is in the code. If you just look at the code hard enough, and maybe have a beer or two, you can reconstruct what this URL is. The question is, can your static analyzer do it? And for that, you need support for loops. Sorry, we don't know what a loop is, but you somehow need some definition of a loop and some analysis of something that you call a loop. And then you have to support for all these arrays, for calculations, and so on. Otherwise, you don't get a value. Now, if we want to know whether a value analyzer is good or not, we have to somehow have a benchmark. We need to have applications where we know what the outcome should be of the value analysis, and then we take a bunch of value analyzers, we run them, and see what their precision is, what their recall is. How many values do they find? Which values do they miss? Which values do they report that are just nonsensical? Now, the problem is that what I've presented you so far is actually a very particular instance of a value analysis problem. Take this code. There are many formulations of what a value analysis could give you here. What we call a precise value analysis would just give you the 10 C's in a row. However, some other analyzers say, well, this is C repeated 10 times, you could say, as a regular expression, or C more than once, which is also somewhat capturing what is going on here, or C 0 or more times, which is also somewhat a representation of what we have seen. And for this example, this is pretty much equivalent aside from the length, but it really depends on your use case what you have. So when we're talking about concrete value analysis, and this is what the benchmark suite I'll present in a minute is about, we're talking about all the necessary informations in the program. So for example, if we did not know how often this loop runs here, then this would probably be the best thing we can do. We're not going to get there if we don't know how often we want to repeat C.
Sorry, can you use the microphone?
Oh.
Sorry,
Okay, no problem. Usually I roam around the place and just scream. Okay, then sorry for all the people on the internet. Concrete values. So, to get these, all of the necessary information must be in the program. The values must be deterministic, so if there is kind of a random number generator, then I cannot give you a value. I can only give you a formulation that says this part I don't know. There should be a small set of possible values, because if I want to enumerate all of them, and there are billions, I might be spending a bit longer than I expect. And a good example of this is obfuscated code, because there was an original value, people just don't want me to know it, so I can reconstruct it and get the original value back. There are other examples like regular expressions where people say, I can tell you what this program formulates as a value, but it's not like one value. It's, I know that this is repeated maybe depending on user input between 5 and 10 times. Totally fine. It can also over-approximate the language. It can deal with parts that we don't know. Then you just have, foo, or you know it starts with F and then there are some O's, and that's it. Or even the last one, it's a perfectly fine representation of the value. It's also a perfectly useless representation of the value. And then there is range analysis that people also use, where they say, okay, we're talking about an array or maybe memory. I know where it starts, I know where it ends, or I know where it starts and how long it is. This is also what you could ask a value analysis. Then you don't want the contents of the memory, you just want to know the ranges. And in this work, what we're talking about is concrete values. We know that there are use cases for the other ones, and there are cases where the other ones are actually better. But mostly for security properties, you're talking about, in Android apps for example, which URL are we connecting to? Do we have a hard-coded key? Do we have hard-coded credentials? What is the block cipher mode that is being used here? And all of that is concrete values. So, now I said if we want to have a value analysis and want to benchmark it, we need a ground truth. There is already an existing tool called JSA and it has a benchmark suite. However, it's far from perfect, because for this code they say we have 3 regular expressions. If your tool is great, it will give you C 0 or more times or null. If it's less good, it will give you C 0 or more times or null. And if your analysis is crappy, it will still give you, you get the point. So neither of these representations is super precise. So this is not what we want in a test suite. Plus, we know that this is never going to be null. Why on earth is it in there? Which means, when we started this work, all we wanted to do is look at the state of the art of value analyzers. And we were disappointed with JSA, and then we said, let's do our own benchmark suite. There must be something better. Because you can get as concrete as you want with your value analysis that you came up with. You might even get a Turing Award-winning value analysis, but in JSA, you get the same score as someone who just says, come on, this is C, like 0 times or whatever. So, what do we want? We want a ground truth with exact values. And we want them to be correct. So ideally, we want the ground truth to be generated automatically from what will actually be computed at runtime. Or else some dude will just write some garbage down and we have to deal with it. We want support for Android and Java because this is what we were interested in back then. And the test suite should contain common challenges. So if somebody has a good handling for loops or for arrays or interprocedural analysis, this should show in the benchmark suite. He should have a higher score than someone who just looks at straight line code without anything. And then we want statistics. If we say you're better in the benchmark suite than that other guy over there, we want to know, why does this happen? Do you have a better support for loops? Do you have a better support for interprocedural analysis? Because only then we can learn from it. So this is what we built out of this. We generated a bunch of test cases in Java code. These test cases are then compiled. And now 2 things happen. So firstly, we run these on the ground truth analyzer. So if it's Java code, it will be run on the JVM. If it's Android code, it will be packaged into an Android app and will be run on an emulator or a phone. And once this has run, you know the value that this test case computes. And this will automatically be annotated to the test case and will become metadata of the test case. You never specify the ground truth, you just write the test case. Plus, as I said, we wanted to know what this is about. Is this a challenge for loop handling or not? Or is this for interprocedural analysis? So the challenge analyzer will make these sort of statistics and will also put it to the metadata.
Now that we have our annotated test case, we can run the different value analysis approaches. So if it's for Java, we put it into a jar and feed it to the value analysis approach. If it's an Android test case, we put it to an APK, run it through the value analysis approaches. The evaluator then just compares the results that every approach has produced with the metadata. And then you know, okay, JSA or Blue Seal or Stringhound or whatever they are good on this and bad on this. And you have a couple of challenges there. For example, the correct handling of fields. We have seen this in the previous talks. If you mess up your fields, you might actually have false positives due to cross-referencing. Or, for example, what about the typical obfuscation style analyses? You have arrays, you have arithmetic calculations, you have loops, you have API calls like arrays to string. If you don't have a model for arrays dot to string, you will not get a value out of this one. And I'm not going through all of the test cases. There are very many that we have in the test suite, and we of course make this publicly available. It is already on GitHub. So when we compare this to test suites that already exist, for example, we find out that we have quite a different distribution of what the challenges are. So for example, to succeed in our test suite, you have to have at least a quite good support of string builder and string buffer, because we've seen that this is what is often required, for example, when handling obfuscation in Android apps. You have to have a good grasp of interprocedural analysis and arithmetic calculations. And now we ran a number of analyzers on that. So the interesting thing is that the scanners where we put an asterisk, they report exact values, the other one report regular expressions. We match regular expressions against precise values by saying if the precise value is in the language of the regular expression, well, okay. We have some special casing. If you just put dot star, we say you didn't find a value, because that would be highly unfair. And what you find here is that many of the approaches actually are quite lacking. So Valdroid is pretty good, Stringhound is pretty good, Harvester is somewhat good. Harvester is a dynamic or hybrid approach that does slicing and then generates a new APK and executes that APK on the phone. Problem is, if something inside that APK crashes because the slice was not an executable slice, you're in trouble, you don't get a value. Or you get a partial value because someone catches the exception and the program continues. So actually this performed on JVM test cases worse than on Android test cases, because the original publication was on Android, but here it was kind of lacking. Stringhound, the paper reports on Android, but the problem is that they don't have the models for executing on Android. So you can actually just run it on the JVM, but not on the actual Android phone, which makes the comparison a bit harder. But nevertheless, you see that there is still a lot of room for improvement in value analysis approaches. And if you just try the old JSA test suite, then you will find that, this is a solved problem. It isn't. This is just because of the crappy kind of ground truth that you see in JSA. Just very quickly, a couple of interesting results. So why should I care about this? This is not complex code. You have a string, a prefix, then you append numbers to it, and then you append after loop. And when you look at the results produced by some value analysis approaches, you will find correct values, but also things such as null, comma, start. Why? Or JSA says, well, I have a regular expression. This is an approximation. It's start and something. Start.something is not helpful. Then in another test case, for example, JSA then again gives us a regular expression that is just super over approximating and not really helpful. Here you have a value that you can either get right or wrong. JSA says, well, you might be right or you might be wrong. Yeah, thanks a bunch, JSA. Blue Seal even says, okay, I concatenate the two. So these approaches, even while this code may sound trivial or look trivial, these are still challenges for many value analysis approaches. As I said, we make this data publicly available. ValBench is on the internet. If you have your own, like, super secret patented, well, no, if it's patented, it's not secret anymore. Anyway, if you have your own value analysis you want to test on this, feel free, report the results. Maybe we can also put a list of current value analysis approaches and how they perform. That would be very interesting. The replication package contains all the generators as well. You can also add new test cases if you want. And this is just a call to have a better evaluation on these tools, because the original papers, they of course said our analysis is great. They didn't say we report a bunch of garbage. At least the sentence was in none of those papers. So thank you very much for your attention, and I'm happy to take questions.
Thank you very much. Now, where are the questions?
So maybe coming back to your evaluation slide where you had all of those different... yeah.
This one.
Yes, exactly. So I was wondering, because you said those without asterisks are actually those that have regular expressions, and it's striking
No,
that other
way around.
Oh.
Those with the asterisks produce exact values. JSA, for example, produces... those with asterisks are exact values. JSA, which doesn't have an asterisk, is one of the core regular expression-based ones.
Oh, that's interesting. Okay, because I was first thinking that the regular expressions save them, but apparently it's the other way around.
No, the problem with the regular expressions is twofold. So, firstly, you can get a useless but correct regular expression like dot star, which is correct but doesn't help anyone. And the second thing is it hides that tools are often unsure by just putting, it could be the right or the wrong or something totally else. This is what you get here. It says null or right or wrong. The right one is in there, but there's also a lot of garbage.
Mm-hmm. Okay, thanks.
So perhaps one more question. You use arrays here. Are these arrays which you take into account always of constant size? Or could there be obfuscation also in that you kind of make these numbers somehow weird?
This is something I would need to look into the data set. So in general, this depends on what your analysis tool can do. For example, Harvester is based on backward slicing and execution. So even if your array size is not constant, that should work out in theory with all the problems of making a slice executable. ValDroid is an approach that slices back and then simulates the code, very much like abstract interpretation. Should work. Stringhout does a cross-compilation from Android to Java and then a simulation. Should work. For JSA, I'm very skeptical.
Okay, thank you very much. More questions, please. So I think everybody's exhausted or happy or both.
Asleep.
So thank you again.
Thank you.